Hello, class 11. I'm sorry you must be waiting for my lecture from quite a long now. So today is 10th April 2020 and we are studying the 6th chapter, Chemical Equilibrium. Yesterday we have studied how to derive, what is the law of mass action and how to derive the equilibrium constant expression for different equations and reactions, and also what is equilibrium constant for concentration Kc and for partial pressures Kp. Today we will study about the relationship between Kp and Kc. What is the relationship between them? How we can relate the two with each other, the Kp and the Kc. So today's topic is the relationship between Kp and Kc. First thing that we all must understand is what are Kp and Kc and why they are so different. K is here constant, C for concentration, and P for pressure. In my yesterday's lecture, I told you that gases are not measured in terms of their volumes. We cannot trust their volumes. So mole per dm cube or mole per liter, the active mass is not okay for gases. It's not okay because we think it's not okay. No, it's not okay because in practical experiments, it's proven that with the value of Kc or using concentration in the equilibrium constant expression, the answers theoretically did not match with the practical yield or practical answers. That's why scientists have given a new constant Kp for the gases. So let's consider a gaseous reaction. Now, gaseous reaction means all are gases. So we have here m mole of A gas and we have n mole of B gas, reversible reaction, X mole of C gas and Y mole of D gas. Now, if you want to write the Kc for this equation, then it's going to be C power X, active mass of C, D power Y, active mass of D, A power M, active mass of A, and B power N, active mass of B. That's how we write the Kc. But since this is not giving accurate answers, so we have to jump for Kp. This is in terms of concentration. In terms of concentrations. Like if you take the quantity of the reactants and products in moles per liter or moles per decimeter cube. Now in that case, the answers, as I told you, they have some problem. So we will prefer to take pressures. So in terms of partial pressure, excuse me for this guy shouting to sell something outside. So for partial pressures, ATM or Pascal or whatever, because that is trustworthy for gases. The constant then will not be denoted as Kc, it will be denoted as Kp. So it's going to be partial pressure of C, power x, partial pressure of D power y, and can you guess here? Yes, PA, M, and PB. And now this is how you represent in terms of partial pressures. So if these are the partial pressures of the CD and AB, the constant will be called Kp. If you take the concentration mole per dm cube of the reactants and products, the constant is called Kc. There's a difference. So these two are both constants, and initially even gases, they had Kcs, then they shifted to the Kps. But right now we are here to decide what is the relation between the Kp and Kc, and to do that we use the general gas law. You know, the general gas equation. Do you know what is it? Yep, PV is equal to nRT, where P stands for pressure, V volume, yeah, moles, universal gas constant, R 0.0821 mole ATM per dm cube Kelvin, and T for temperature, Kelvin. Must be in Kelvin. Now here, can I change it to this, like P is equal to nRT upon V? What do you call it? Cross multiplication? Okay. Can we write it like N upon V into RT, if you don't mind? Do you? No? Yep. Now what is N upon V? What are the unit of N? Mole. And V? dm cube. Oh, here you can observe that N upon V is some numbers, moles per dm cube, mole per liter. So N upon V basically stands here the molar concentration. So if you talk about, if we take reactant A, okay, then PA will be equal to N upon V of A, which is the active mass of A, RT. So same, but where there is N upon V, we write the active mass of A, because N upon V shows the active mass. So PB, can you help me here? Yes, active mass of B and RT. Similarly, for PC, yeah, can you guess? Active mass of C, RT, or PD, active mass of D, RT. Again, if you are confused here, so I will rewrite for you. The main formula is P is equal to N upon V RT. This is the formula which we derived here. Now, if you replace N upon V by the active mass of A, that shows the pressure of A. Okay? If you replace N upon V with the active mass of B, that shows the pressure of B. So on the two, right? So can I put them in equation number 2? I can put them. PA can put here, can be put here. So we do what? We substitute. We can say substituting the values of PA, PB, PC, and PD in equation number 2. So what will equation number 2 become? Equation number 2 will become, Kp remains Kp. What PC becomes? PC becomes CRT. But the PC whole power is x, so whole power is x. Is it okay? Do you mind? Is it okay for you? Yep. And similarly for BD, we write active mass D RT whole power y, and denominator PA active mass A RT whole power M, and here active mass B RT whole power N. Now the whole power X is going to go to every whatever inside. So Kp is equal to, guys, C power X, right? And RT power X. Here D power Y and RT power Y. And if you go down, it's going to be A power M and RT power M. Likewise, B power N and RT power N. I'm sorry, it's a bit longer here. From this, it's just a second equation. I'm replacing the PC, PD, PA, PB with these values and then distributing the powers. Now here, if you don't mind, I will want to write the C and D together and R and B together, because RT, similar base. From mathematics class metric, you know, when the base are same, the powers are added. Down here as well, when the base are same, power are added. So this equation can be transformed. I'm sorry, I have to go to the next page. So I hope you remember it and I hope I remember it. So we can just change to the next page, and here we see what we see here as Kp is equal to okay, C power X D power Y, and RT, similar base, power are added, X plus Y. Down there, A power M B power N, and down there RT powers are added, M plus N. Now this is, I hope that we're on the same page, but it's like there were 2 times RT as at the numerator with the power X and Y. So we wrote 1 times and we do X plus Y. And as the denominator, there was 2 times RT with power M and N, and we just wrote 1 time and M plus N. Now, did you observe this thing, that this guy here, this quantity here, C, the product of active masses of reactant divided by the product of active masses of earth, is called Kc, right? So this is called Kc, this whole. You know this, and it's also here. Kc is, this is Kc. CD, AB, KC. So we can write here like this. This whole goes Kc. How about this guy? Again, base is same, powers they're dividing. So what you do, what you know from class metric? Yeah, throw at me. Yes, X plus Y minus M plus N. Now, because the powers go up and then they go subtract. This, if here we X plus Y minus M plus N, we denote it with another number delta N symbol. So what is Kp is equal to now? Kp is equal to Kc RT power delta N. This is mathematical relationship between Kp and Kc. Now, don't worry, the delta N, you know, delta N is the kind of index, a number, a value with after the subtraction of these two. Let's take it to a practical case and then you will understand, right? The Kp-Kc's relationship, right? So, case 1. Look at this reaction. H2 gas plus I2 gas. Double arrow, 2Hi. Now, my dear fellows, my dear friends, ladies and gentlemen, X plus Y is basically the sum of the moles at the product side. There's only one product. So x plus y is 2. And m plus n is the sum of the coefficient for the reactant. So 1, 1, 2. So x plus y is 2 for this reaction. So this is x plus y, right? And it's 2. These two make m plus n. And this is also 2. So if you put this in this equation, Kp is equal to Kc RT power 2 minus 2. So the delta n is 0. Something power 0 is equal to 1. So it means that for this reaction, Kp is equal to Kc. The value of the equilibrium constant at partial pressure and also at concentration will have the similar value for this equation, because the moles of both sides, the sum of the moles, sum of the coefficients on both sides are same. So delta n becomes 0. So when it becomes 0, then this value has a power 0. Even the entire value equals to 1, so Kp is equal to Kc. Kc into 1, Kc. This is the relationship. So any reaction in which reactant side coefficient, the m plus n, product side coefficient, the x plus y, subtract them, and answer is 0. Delta n is 0, Kp equal to Kc. In simple words, when volume on both sides are equal, the Kp is equal to Kc. Our book has a very simple line: when the volumes on both sides are unchanged, then Kp equal to Kc. But I have given you a little bit extra detail for you, and I know it's going to help you. If you write this in the examination, it will really make sense, and you will get a better understanding of why this is happening, other than just cram it. Okay? Let's apply on a case 2. Right? In case 2, we take another expression or equation. Let's say 2NH3 and double arrow, and you have N2 plus 3H2. So there are 2 ways to guess. Volumes on this side, 2 volumes. Volumes on this side, 2, 3 and 1, 4 volumes, sorry. So this is 1 volume, 1 is the coefficient here. Here, 3 the coefficient here. So 3 and 1, 4. So when you do 4 minus 2, the answer is 2, positive 2. Okay? Let me write for you. Kp is equal to Kc RT power 4 minus 2. So Kp is equal to Kc RT power 2. This is positive power. Delta RT is a number, and when you square it, it gets even a bigger number. When a bigger number will multiply Kc, the product will be even bigger. So Kp will be much bigger than Kc. Right? The value of equilibrium constant and partial pressure for this reaction will be much, much, much bigger than the value of Kc for the similar reaction. Because the RT is a value, R is a real temperature, T is real temperature, R is the universal gas constant. If you multiply them and you square them, you have a bigger number. The bigger number multiplying the Kc, the product Kp will be bigger. So Kp is bigger for this reaction. You can guess in 2 ways. You can just write when the volume of the products are higher than the volume of the reactant. So you can say when the sum of coefficient of the product are higher, which is x plus y is bigger. In this case, x plus y is equal to m plus n. That's why Kp is equal to Kc. In this case, x plus y is much greater than m plus n. That's why Kp is greater than Kc. The third case, you do yourself, right? You can take the book's help, but do it this way. And tell me why is Kp less than Kc. Because in the third case, you will see the x plus y will be smaller and m plus l will be bigger. This power will be negative, and if it is negative power, then the RT must go down as denominator to make the power positive. But doing so, it will divide, not multiply. So when multiply makes the power bigger, division makes the quotient smaller. So you have to write it in this way and tell me whether you liked it or not, whether you could do it or not. So there are two ways of relating the KP and KC. One way is just telling that when the volumes are increasing, decreasing, KP is increasing, decreasing, or remain same. Other way is rather more technical, which explains in more depth. Here, we have seen many questions in the examination. Like I have a paper of 2019. It's last year's paper. In the last year's paper, this question, you can see this long question. State the law of mass action, derive expression for Kc for this reaction. See, you will say, I wish I would give this paper. So this is always very easy. Students just they don't study, and then in the end they are stuck copying this. Look at the B. What do you understand by Kc and Kp? Describe their relationship. So what is Kc and Kp? Then how can you relate? It's a long question, 7 marks. So if in a long question, 7 marks, you end up writing just this KP-KC relationship. I mean, that's not right. Okay, just this 3 lines it doesn't make sense that much. So we should just define KC and KP, and then we should simply write the whole relationship here, like I have told you. So you see, this is the paper 2019, and you can see how easy is the paper and how difficult we think it is. Anyways, it was a good day with you once again, class 11. I'm very glad to see your copies, and it really makes me feel good. Everyone is trying to make as better as they can, in which they are learning and investing their time in a good activity. We will end our lecture here. I will check your homework by tonight, and tomorrow and day after, the weekend, we will not be working, so you can enjoy at home. And we will now meet after the weekend on Monday with more exciting lectures and class. Thank you so much. Have a good time. Goodbye.